My name's Aaron, and today I'm going to talk about how to make Cassandra repeatable, scalable, reliable, and observable. But really the talk is about how to make the process of taking a software solution from your laptop into a data center environment a repeatable, scalable, reliable, and observable process. Because that's what we want to do. Take stuff, the awesome stuff we do on our laptop, and make it run on big systems. A little bit about myself before we get started. I'm the co-founder of a small company called the Last Pickle. We work with customers to deliver and improve Cassandra-based solutions. I'm a committer on Cassandra. The other people we work with have been using it for 4 or 5 years as well. I live in New Zealand, and we have some people in the USA. So when we talk about delivering software, there are some basic steps that we go through. We do design, we do development, and we provision some hardware, and then hopefully everything's running. So let's look at what I think we should be doing as we move through this process. Start with design, and start with the data model. Most of the problems to do with scalability start with the data model. You should be using no-look writes when you design the data model. Just write it. Cassandra will soak up those writes in memory. Some of them will get down to disk, and we'll compact them away on the SS table. Don't do a read beforehand. You should understand how big your CQL3 partition is going to be. I use the phrase that it should be bound in time or space. So if you're doing time series data, how many points are you putting into each bucket? Is it 1 day? Is it 1 week? Is it 1 month? How big is that going to be? Choose something that makes sense for your query techniques. We generally read data by the week, so let's make our buckets 1 week. And if you need to constrain things in a different way and you don't have time series data, let's say you're making some custom secondary indexes, you can use an old-fashioned hash and modulo and shard a row. So again, you've got an idea about how big these partitions are. You don't want to be the next person in the next talk I do when I say that you win the biggest partition competition, which now stands at 12 gigabytes. You want to avoid mixed workloads on a table. For example, the user signs up and you store some initial information, and every time they log into the site or visit the site, store that on a different table. If you're putting it on the same table from when they signed up, you're going to get row fragmentation. Over time, that is going to have a reduced read performance. Be mindful of tombstones. Understand that deletion process in Cassandra, and understand if you're doing a lot of deletes, are you using the level compaction strategy? You probably should be, but you probably should be doing it if you're using SSDs. If you're not on SSDs, you might not want to use it because of the additional disk I/O. If you've got a system and you think you want to do a lot of deletes, maybe you could borrow a page from Kafka and have the clients have some sort of offset. And then they use that, and you use TTLs, and you use partitioning and things so that you don't have deletes in your read path. Later on, I'm going to look at some metrics, and I'm going to tell you how you can understand how many tombstones are getting touched in each read. As you're going through the design process, be mindful of consistency. Consistency impacts availability. We know that from the CAP theorem, but it also impacts performance. If you're designing something and at that point you say, well, hey, this is going to work with eventual consistency, write that down. If you're expecting strong consistency, quorum, note that. If you need to use lightweight transactions, linearizable consistency, note that as well, so that the developers know, hey, we can make this go faster because we only need to use CL1. And lastly, you need to create a parallel data model. In the parallel data model, when you add more nodes to the cluster, you improve your throughput. The classic example of an anti-pattern in Cassandra is a Twitter clone that has a global timeline. No matter how many nodes I put into that cluster, there will only ever be 3 that can process the writes on the global timeline if it's 1 row, 1 partition. That's an anti-pattern. Have a data model so that if you are successful and you've got to scale up 10x, you increase the size of your cluster and you improve your throughput and everyone's happy with you. as part of designing your data model, I think you should design the environments that your system is going to run in. A dev environment, a QA environment, a live stage environment where you can put software, test integration points, and then move on to a live environment. And as you're designing those, think about, well, is this persistent? Can I run this on AWS or whatever and throw it away? What sort of availability does this need? So for dev, it might only need RF1. Obviously at live, we might be RF3, and we might be RF3 with multiple regions and all sorts of things like that. And what sort of performance do I need? And if I get the configuration management right, all this is easy. All this is just role tagging on nodes to tell me, oh, I've got 3 Cassandra nodes, or I've got 30 Cassandra nodes, and because I'm deploying QA, I'm not going to deploy Riemann for monitoring. We'll look at that later on, or I'm not going to do this or that or the other. Now, as you're getting into designing these environments, you're going to start to think about high availability engineering. So for all the things that are Dynamo-based, like Cassandra, a bit of Zookeeper perhaps, some Kafka and things like that, generally there's 3 availability zones, or racks, or whatever it is, 3 somethings, 3 places where things can fail. In Cassandra, of course, our HA engineering means we want to have a snitch that's aware of the rack. So the EC2 snitch turns the data set, the availability zone, into the Cassandra rack, or the gossiping property file snitch. And when you pair that together with the network topology strategy, it means that Cassandra will try to place a replica into each availability zone, or into each rack, or into each whatever it is you decide is the bulkhead between failure. So when you do lose one of those AZs, you can keep on going. And you're always going to have systems that aren't Dynamo-based. Hopefully the middle tier is stateless, but you're going to have some monitoring tools, you're going to have all sorts of other things around. We want to understand the failure scenarios, work out what's going to happen when they fail. All right, I might have some instances in AWS that I've stopped, and I'll be able to spin them up, and they'll take an elastic IP, and then I'll get my monitoring back. Or I'm on premise, these things sit on some high availability virtual infrastructure, they'll be okay. So we move through design onto development. I group all of the DevOps into this because it's all just dev work, as far as I can tell. We want to install package-based installs. We know that they work. If you're rolling your own, or you're taking the bin and you're installing that, stop doing that and just use the package installs. They work. And when you do that, pin the version so that you don't accidentally upgrade your cluster. Because I've seen that happen a few times. It's kind of one step worse than running out of disk space, I think. It's always good if you could have an internal repo for your packages, so that, again, think about this for high availability. Oh, we can't spin up any nodes because the repo we went to get that thing doesn't exist anymore. It's down. So we have to wait for them to come back up. There goes all of my high availability planning because I've got this external dependency on someone else. Onto the application. Developers should know how much data they are reading out of Cassandra. Now, Cassandra 2.0 helps because now in the native binary protocol, there's a paging system. So we'll automatically pull, I think from memory, 1,000 SQL3 rows at a time, and then page that and get the next 1,000. So it's a little bit harder to break things. But if you don't understand what it is you're reading, you could still send crazy queries, things that read lots of data. You just have to be mindful of it. Don't take an input from the user and use that to set limit on your request. Again, use that appropriate consistency level. Understand that at this point, we can use CL1, and look in a minute why that's awesome, or we have to use lightweight transactions here because this is sign up, and we only want to have one user called Bob. Now, if you can do this, use the token-aware load balancing policy, use that with asynchronous requests, and use a consistency level of 1. That will take all of the internal network traffic out of your synchronous request process. Your client then essentially becomes an outer ring in the cluster, It sends the request to one node who will be a replica, and they will answer that with local disk. And your client can then do a scatter-gather process. It can send out 10 requests and wait for 10 to come back, and then move on to the next thing. But if you're doing that, don't DDoS yourself. Don't write code that sends 1,000 requests and doesn't bother to see if they finish. In fact, don't write code that sends 1,000 requests at a time. Send 100, wait for those to come back and get to the next 100. Because there's probably more than one client thread running at a time. And what looks good to one client thread often looks bad to all client threads. If you're a misbehaving client thread and you're sending huge requests, either async or batch or whatever it is into the cluster, you're quite possibly impacting the overall throughput, which makes other client threads feel a bit unhappy. I think as part of the development, as part of doing the DevOps, we want to design the monitoring. So we can get that in there and know it works, get that into the QA system. If you need to do any sort of performance testing, you want this in place. For monitoring and alerting, the overall thing is use what you like and what works for you, and don't get too hung up with different technologies. Some of the things that we like, Ops Center, it has some useful things in it. Riemann is great for what's happening right now. You can dump so much traffic through that. Grafana and InfluxDB, which runs a bit faster than Graphite and is easier to install, and it has a Graphite compatibility mode. You can chuck those together. LogStash on the Elastic, whatever it's called, the ELK. So LogStash is kind of like Splunk. It allows you to bring all your logs together and do some log analysis. You could look for degenerate logs and things, logs that are changing a lot. Sensu is a great thing for monitoring processes. If you've got Cassandra running or you've got your middle tier app stuff running, what happens when it crashes? Like, who restarts it? And do they restart it continuously, or do they just do it twice or 3 times and then say, well, look, that didn't work, so I'm just going to leave that alone? Hopefully the later one. So if you're doing monitoring in Cassandra, you're going to be using our metrics library. Well, it's not ours. It's the Yammer metrics library created by Coda Hale. Cassandra dumps some awesome metrics in there. And it's really easy to get them out now. So since version 2.3, just through a configuration file, you can tell Cassandra to automatically push metrics out. And it can push out to Graphite and Ganglia and Riemann and CSVs, and I've even seen one out there for Splunk. These are just reporters in the Yammer metrics library. The metrics that come out have a dotted notation. This is org Apache Cassandra metrics, and then there's a bunch of other things underneath that. If you're unsure about what ones are available, you can connect JConsole and have a look at what's in, because these are also exposed as beans, Java management beans. You can have a look there. If you've got InfluxDB, you can push it to InfluxDB, connect to that database server, and Influx has like a little web UI, and you can list all of the metrics that it's got. So if we want to understand throughput, we can look at org Apache Cassandra client request, write latency 1 minute. This is the exponentially decaying 1 second throughput. So just the kind of the same process as you have for the Linux load. This is 1 second throughput. You can look at it at the cluster level, and you can also look at it at the table level. Now, there's not going to be too many surprises here. If you're writing at RF3, there's going to be 3 times as many writes happening per node. But it's sometimes useful to have a look at it and say, hey, look, nodes are actually doing 50,000 writes per second. That's kind of nice. You might want to put some alerts on that. If this goes way outside of what you expect, if something happens and no one notices and your load goes and your throughput goes up 25%, it might be nice to know what's happening. Same if it drops a lot. Maybe something else upstream is broken and an alert didn't pick that up, so we can alert on the database. Latency is probably the most important one that everyone cares about, and the metrics library provides a lot of latency metrics. It gives us the 50th, the 75th, the 95th, the 98th, the 99, the 99.9 percentiles. So you can grab all those. There's averages and standard deviations. This one here, OACM client request, is the cluster level latency, end-to-end request latency for processing your request. And we also have the local latency. The OACM column family, this gives you what happens when the write or the read thread takes the message off the queue and starts running it. So the difference between these two is normally pretty small. And that difference is network latency internally and queuing and things like that. As your cluster starts to approach maximum throughput though, hopefully the local latency stays relatively the same and we spend more time sitting in queues. And so the cluster latency goes up. And that's the whole point of the staged event-driven architecture. Because we don't want the disks to fail, because when they get overloaded, their failure mode is kind of exponential rather than linear. Now, the timeout for reads nowadays is 5 seconds, and the timeout for writes is 2 seconds. I think a read above 1 second is quite a long time, because that read often can take about 300 microseconds locally if it's a small read. So I would set some alerts on read latency and write latency, and as you learn how your system goes, you might turn those up or down to different settings, but have something to start with. Now that read path is kind of complicated. It's a lot more complicated than the write path, but there are ways you can look into it and see what's happening. At the per table level, we know how many live cells we pulled off disk. That's the live scanned histogram. So that will tell you at the 95th percentile, reads were actually taking this many cells off disk. So if developers are not paying attention to how much they're reading, you can look at the cluster and say, hey, we read 500 columns or 500 cells at the 95th percentile for a request. Is that right? Are we meant to be pulling that much data per request? And we have the tombstones. So early on I was talking about be aware of tombstones. Sometimes you could look at a cluster and you might see that, I've seen this, that the number of tombstones scanned is about the same as the number of live cells. So half the work we're doing to pull stuff off disk is wasted because we just pull those tombstones off, make sure that they delete the stuff they're meant to delete, and then throw them away, basically. And the last one here, the SS tables per read histogram, tells us how many SS tables we touched at the 95th percentile, so it might be 3 or 4. This has to do with the row fragmentation and a few other things like bloom filters and such, but mostly row fragmentation. If it's above 4 on the size tier compaction strategy, that means we're over a couple of tiers. And if it's above sort of 1 or 2 on level compaction strategy, that means level compaction strategies have fallen behind, or we have a lot of data. These are good metrics to look at to give you a view of what's happening in your read path. Often when people come to Cassandra, they want to know, how do I know how far behind a replica is? And I say, you can't. We don't track it. It's not like we're doing a log replay to the replica and we can go back and tell you, oh, we're this far behind. You've got one node in amongst 50 and you want to know, compared to the other 49 out there, how far behind is it? We don't know that. I can give you kind of a gruff guess though. I can tell you how many hints we've stored. OACM storage total hints. Hints are stored when a node failed to, when we either didn't send the write out or we sent the write to a replica and it didn't come back in time. We can look at how many hints we've stored on a per replica basis, that second one. So if we had graphing that, we might see that one node's getting lots of hints stored against it, none of the others are, so something's wrong with that one. And lastly, we can look at the timeouts that are occurring. So I said there was 2 places that we store hints. When we start a write request, if a node's down, the coordinator will store a hint. If the node's up and we start the request and it doesn't come back before the RPC timeout, then we also store a hint. If you've got a situation of a multi-data center installation, tracking total timeouts is a good thing because it's probably, most of your problems have to do with the VPN or the WAN or whatever it is you've got between those 2 DCs, and that will let you know that messages aren't going back the other way. And I've seen that be a useful thing. Some other areas around consistency are read repair. So read repair is a process that repairs data when we read it, and it works in two modes. The background read repair is controlled by the read repair chance and DC read repair chance property that you set on the table. What this says is for a certain percentage, and by default it's 10%, in the background read more data than we need, but don't delay the client. In the background, check to see if it's inconsistent and repair that consistency. Every time we find an inconsistency in the background, we'll increase this first counter. And you can see this if you do node tool net stats. You'll see it pop out at the bottom. The other way that read repair works is a blocking mode. If you do a read at a consistency level above 1, the coordinator checks to see what data those replicas have sent over. If it detects a difference, then it repairs it. And it repairs it while you, the client, are sitting there waiting. So that is our inconsistency actually coming to bite, because now your read request is actually run twice. Your latency is going to spike. So if you're looking at those two numbers, you get an idea about how inconsistent your data is. And the last one I throw on here is not really about consistency, but the speculative retry that Jonathan mentioned this morning. This basically means, hey, I sent a read over to a node and it didn't get back by default within the 95th percentile of how often these things normally get back to me, and so I had to do it again. So it's not that there's inconsistent data, it's just we don't know what the data was going to be. And when we get timeouts, we send errors back to the client, and we track that. We have timeout errors and we have unavailable error. The unavailable error happens when there's not enough nodes when we go to start the request. Timeout happens when we started the request but not enough nodes came back to us, less than consistency level nodes. So we track those at different rates. And we track whenever there's an unhandled exception in the code base. You'll see that when you do node tool info, it'll tell you the number of exceptions. If you get any of these, I think you should alert on them. It means that either your cluster is overloaded or there's a bug in Cassandra. And you probably want to know about both those situations. Disk usage, you can get the total node load from storage.load.count, and you can get per table. It's always good to have a feel about what tables are taking up the most data. Sometimes it's something that people don't expect, and that leads to discussions and discoveries that there is a bug in the code because we're writing a lot of data somewhere we didn't think we were. Compaction can always be a pain. You can get the total number of compactions. You can get the number of compactions pending on a per table basis. So you understand, again, where is the pain points? Whoops, we didn't realize we were writing to that table. And you can get a rate of how many are completed. I should change that. It shouldn't be 1 minute because there's not going to be too many completing in 1 minute. It should be 15 minutes. That'll give you a much better feel for it. And I think that if you've got more than, say, 200 compactions, you should raise an alert. Now, as you're going on, you'll learn what your system's like, and you might not want that number there. Compaction falls behind and catches up. It's not that critical unless it's impacting your read path. And we know we've got this thing called the staged event-driven architecture. There are a number of thread pools, mutations where we do writes, reads where we do reads, replicate on write for counters, and request response is where the coordinator does its coordinating. If we're getting pending tasks backing up, that means we are starting to move to our peak throughput. And once we reach peak throughput and we start dropping messages because we're not able to complete requests in the RPC timeout, we start tracking those here as dropped messages, and we want to alert on that as well. On to provisioning nodes. Whether it is AWS or physical infrastructure or anywhere in between, once you get new hardware, you should have some sort of smoke test that allows you to test your basic assumptions about that. You should have a look at this talk that Toby did last month. He's been working on this stuff for a number of months, called disk latency and other random numbers. He did a lot of benchmarking on what to expect on different disk infrastructure. He has a library that wraps the FIO benchmarking library. He calls it FIO, and he has a bunch of information there that allow you to do a quick test on your hardware to make sure it actually works. The next smoke test you should do is Cassandra. The Cassandra stress tool in version 2.1 is really, really good. It has lots of great options on it now. These options here, the first one says do a write and use a replication factor of 3, the default is 1, and use a consistency level of quorum, and use the native binary protocol and prepared statements in CQL3, and just run that. And we're not trying to do a performance test, we just want to make sure that it's somewhere sane. Like, test that Cassandra works. And we can do a read test and we can do a mixed load test of 1 read to every 4 writes. Now, if you're getting quite skilled at this, you can make the Cassandra stress tool test your own personal schema. Again, the idea of the smoke test is just to make sure that things work, not a performance test, but if you're already doing this, you should bring this into your smoke test process. There's a blog post about this on the DataStax site called Improved Cassandra 2.1 blah, blah, blah. And we should have runbooks. The idea of a runbook is to say, let's plan now for things that we can reasonably expect to happen. And your runbook should answer these 3 questions. Why are we doing this? What are we going to do? And how will we do it? When we write these, we break these up into phases because inevitably people get interrupted. So break it up into chunks where they can walk away from it and come back to it later on. And at the end of those phases, describe the state of the system so that when people come back, they can very quickly remember what they did. So it might be, at the end of this phase, there'll be 4 nodes that are configured to join the cluster. Inside that have tasks that are easy to digest and that they have checks and rollbacks. For example, we're doing an upgrade. We have to run node tool SS table upgrade. We want that to go faster, so I'm going to disable compaction throttling using this command line. This could impact read latency. If it does, here is the command to run to roll that back so that you can hopefully get back to the read latency we had before. That is what a good runbook does. It tells you those sorts of things in a cut and paste way. Just grab it out and put it in. And they're a lot easier to work out the month before you deploy your software than the month after. Once you've got runbooks, the next thing to do is practice them with fire drills. The simple one, short-term node failure. If you're introducing Cassandra into your organization, this is the simple one that just says, hey, look, it works, right? You get some Oracle, some Microsoft, or whatever DBAs, and you run some Cassandra stress, and then you just go and turn the node off, and you say, look, it still works. That doesn't happen too often on your products. If it's down for less than the hint window, we're going to rely on hinted handoff. When it comes back up, there's no action. But that should be documented in the runbook. Short-term multi-node failure. This is essentially break the cluster. Again, this is a learning exercise for the ops team. Take a node off. Okay, it still works. Take a node off. How many nodes did we have to take down until it failed? And how did it fail? And what did that look like to the application? If this was me in production, I would generally come back from this and run repair with a -PR on every node because who knows what's gone on. And I would disable the hints because I don't need those running anymore. Disable the hint delivery, sorry. Lose a whole availability zone or rack, whatever it is you've got there. Again, for less than the hint window, we should still be available for quorum operations if we designed that high availability engineering just right. And when that happens and you bring it back up, you could allow the hints to deliver because we're inside the hint window, which by default, sorry, is 3 hours. But given the amount of effort that those hints have probably gone through, you could disable the delivery of hints and use a repair on those nodes. Next thing is a medium-term failure. So hint window is how long we record hints for after a node has gone down. If a node is down for less than GC grace seconds, we can return it to the cluster. The next step is for when it's longer, and we'll find that one out. So we can bring it back into the cluster, but we can't rely on hints, so we have to do a repair. Again, while it was down, we could still do quorum operations. When we bring it back into the cluster, we do a repair without the -PR because we want to repair all the data on that node, not just the data in its primary token ranges. The next one is a long-term failure. So when we're down for longer than the smallest GC grace seconds, GC grace seconds by default is 10 days. It defines the minimum amount of time that a tombstone should exist on disk. And if you do a repair or something like that inside of that period, we will redistribute tombstones to make sure they are sent over as part of that repair. So that means deletes get distributed and data doesn't come back to life. If a node's down for longer than GC grace seconds, then it is a dead node. You cannot bring that back in. You risk having zombie data come back, so you have to replace it. There are some options on the command line about how you can replace that node in an easy way. Check the documentation. We've done the bad ones, now do the kind of exciting ones. Maybe you could start with these if you wanted people to feel good about themselves to start with. A rolling upgrade is just a repeated short-term failure. That's all it is, with the added excitement of changing the software as you go. So do that as a fire drill. A good one is deploy the revision from before the previous revision to the one you want to run on, and then do an upgrade. Rather than deploy 2.0.10, deploy 2.0.9 and then upgrade it to 2.0.10. Scale up. This is where we move to bigger hardware. Again, this is just repeated short-term failure. We turn the node off, we copy all its data and config onto a new node, we turn it back on. Good to practice. And scale out, we do this all the time. We're available for all operations. This is the easy thing. This is why people go to all the trouble with Cassandra. So that's all I have. I've got about 2-3 minutes for questions if anyone has any. Yeah, at the front.
In terms of tombstone.
Yeah. Hang on a sec.
I'm just wondering, removing a whole table.
Yeah.
Would it be better performance compared to moving, or you will still end up with the same problem with the tombstone at that point?
So the question is it better to remove a table than do deletes? That can work if you've got kind of a data windowing and you have like one table per month. That sometimes still works. Often though, it would depend on the use case. But if that works for you, you've got a windowing thing and you have one table per month, then go with that. Yep. Any other questions? Yeah.
When one of the data centers was down and you are bringing it up, you probably will do a repair. So first question is whether you have to do it on all nodes, or another one is whether you do a range repair or just a regular repair in that case.
So the question is, when your data center goes down, how do you do the repair to resolve it? Node tool repair in the later editions, 2.0 and above, allows you to specify the data center that you want to repair from. So you could bring it back up and say repair from the other one, don't repair from the data that we don't have. And whether you wanted to do sub-range repairs depends on really how much data you've got. You do though, if you're doing a repair and you know you're going to run it on all the nodes in the DC, you use the -PR, so it only repairs the primary data on that. I'm sorry, but that is all the time I had. I've been instructed to let you know you should go immediately to your last talk, and I'll be around if you have any other questions. Thanks.